I want to present Dr. Luis Uccellini, Director of National Centers of Environment Prediction, NCEP, the National Weather Service, the National Oceanic and Atmospheric Administration. Luis Uccellini is Director of National Weather Service's National Centers for Environmental Prediction in Camp Springs, Maryland. He received his PhD in 1977. He has published over 60 peer-reviewed articles and chapters in books. He has received many awards and recognitions of his research and operational achievements, including the Maryland Academy of Science Distinguished Young Scientist Award, NASA Medal for Exceptional Scientific Achievement, American Meteorological Society's prestigious Clarence Leroy Messenger Award, National Weather Association Research Achievement Award for significant contribution to operational meteorology. In 2001, received his U.S. President Meritorious Executive Rank Award, and in 2006, he received the U.S. Presidential Distinguished Rank Award. So we're happy to have you.
Now, with all those awards, I hope I can find my talk in here. Is that session 3? Okay. Still loading. Loaded before.
It's opening, but it's a very big file.
Yeah,
so.
yeah. So, there it goes.
Oh, okay.
Okay. Well, first, again, I'd like to thank those who invited me here, and Pinkas and Hadas. I really appreciate the opportunity to come here. This is my first visit to Israel. It's been an eye-opening experience in many ways. It's been a very enjoyable visit. What I would like to do today is, it's similar to yesterday's talk for those who were there, but not identical. So I want to speak to advancing the prediction of weather and climate, including the forecast of extreme events. And in a sense, sometimes I think we don't take a step back and make a realization of the amazing advances that we've made in weather prediction, especially over the last 30, 40 years. And actually it just goes to show how long it takes to really make the advances in these types of difficult problems. I'll then speak to the NCEP numerical models, the weather and climate model, the forces for change, types of activities that are ongoing right now that's allowing us to extend our predictive capabilities across an entire Earth system, and then take these predictions for decision support based on prediction capabilities. And I guess this is one of the major changes that's occurred over the last 15 years, where people are actually now relying on our predictive skill to make important decisions, whereas these same people basically ignored us and just treated, almost treated us like a joke in terms of making forecasts, especially beyond 24 hours. So where were we in the 30s and 50s? This is really taken from a novel that was written in the early 40s by George Stewart called Storm. This individual spent about 3 years in a forecast office, actually spent a full year working in the San Francisco forecast office. And then the whole book's on what happens when a storm crosses the Pacific and affects the west coast of the U.S. So you get a sense that it was a very subjective. This is when meteorology was considered an art rather than a science, very subjective. They relied on surface data, increasing use of radar data after World War II. Like I said, very subjective, based on experience, analogs, that kind of an approach. There was actually, when you read this book, the big arguments on the forecast table was the polar front theory, which I was kind of amused about because we just accepted that as, but that was the new conceptual model, and it was very, very controversial. You get into the 1970s, and numerical modeling now was being introduced over the last 15 years. I remind folks that numerical models were not accepted when they were first introduced. And you can even see in this chart where a situation like a heavy snow event, a very synoptic scale type event, had a predictive skill. This is from Cressman's 1970 article of 12 hours. And this is what I grew up with, the notion that you couldn't make a forecast beyond 24 hours. And I've talked with my colleagues over the last 20 years, and we still pinch ourselves when we look back on where we were and arguing whether we'd ever be able to make a credible forecast at day 2. So here we are. This was actually being written in a bulletin about abandoning research that uses weather sequences generated in a computer. Now, for those who are in the climate debates, this should look familiar. Just substitute climate for the word weather, and you get some of the climate skeptics, okay? So this is what the weather community was facing. And of course, in the 1980s through the present, we just plunged ahead. We now have the full establishment of a global observing system and global models, actually helping to dictate the structure of the world's largest computers. So, and those two things, those are the three pillars, really: global observing, global models, and computers. So today's forecast process, we have a multifaceted type observations. You see here just examples, marine observations. The aircraft data is becoming increasingly important, but you notice that they tend to be concentrated along singular routes. So you have an oversampling problem. Aircraft data has a warm bias, but you get data every 5 minutes. Okay, so there's a strength and there's a weakness. Satellite information, obviously global coverage, but you get very thick layers. You don't get very specific data points. So there's our strengths and weaknesses. And of course you have the radiosondes, and you have microwave precipitable water. Lots of different types of data. GPS, I should add that to here. GPS, the cosmic-like data, is becoming increasingly important for numerical prediction systems. The forecast process is objective. It's based on numerical models, initialized with a cube of data. We've gone from the single surface up to a full cube. And we are now forecasting nationally down to local offices. And in the U.S., we have that combination of national and local offices that produce the full forecast. So our challenge is we're now working towards this Earth system model approach. I'll get into that more. And then the assimilation of satellite data. Obviously, that's becoming a key part of the global observing system. And the challenges of extracting the information from this data while avoiding its weaknesses are immense. So now we say, I could sit back and show a whole bunch of statistics, but one of the other things that I grew up with was you cannot predict the extreme event. Don't even, in fact, in the weather services, there were edicts written that you shouldn't even attempt to predict extreme events because you just didn't have the capabilities of doing that. So we had situations like this. We have this incredible storm off the west coast of the U.S., very fast deepening storm system. Those central pressure points every 6 hours. This storm was not predicted at all. And in fact, the analysis, the real-time analysis for this would not even have that storm system out there, even as it was spinning up off the West Coast. So Reed and Albright wrote a paper on that in the mid-'80s about the rapidly developing storms over the marine environment. Today, well, January 2008, a major storm event off the West Coast. We have almost 10 feet of snow in California, localized flooding, heavy rains, rainfall amounts of 2 to 10 inches. Now, what's really interesting about this is the Climate Prediction Center was actually pointing to the potential of major storm events off the West Coast 3 weeks in advance, because they've now operationalized the MJO and what it means for either shutting down the weather or enhancing extreme events. And they actually wrote on December 24th about the potential for heavy precipitation events by week 3 along the west coast of the U.S., 3 weeks in advance. You get into the 6 days prior to the event. They do a hazards assessment. A 48-hour QPF, quantitative precipitation forecast, issued 5 days before the event, puts out, close to 6-7 inches of liquid precipitable water. So the forecast community is clearly, in this case, you see extreme event, forecast weeks in advance, in a sense, but more specifically, a week in advance. Okay, now we have convection. This was probably the largest convective outbreak in the United States, one of the deadliest, 330 fatalities. It involved over a quarter of the country, 148 tornadoes. The magnitude of this event, this started like about noon. The magnitude was not realized until the evening, even amongst the meteorological community. So even as it was happening, people knew in individual locations. We did not have a full appreciation of this event, even as it was happening. So we go to the, this is the Super Tuesday. This was when one of the primary dates, I think this was the date that Barack Obama really got to the top in the Democratic Party. That's why it's called Super Tuesday. 63 tornadoes, 57 fatalities. And so the folks who study this kind of decision-making amongst the social scientists, you see, we had outlooks issued 6 days prior to the event, probability of detection 100% in all of our watches, an average warning lead time of 17 minutes. We had the emergency management community all, working together a day before this happened, getting communities ready, and still 57 people died. Why? This is where the social science community is coming in. And there are some feelings that if you extend a warning lead time too long, people will go to a shelter and then come back out. Or they'll drive to get their family out of school rather than stay where they are if they think they've got enough time. So we're working those kind of issues, but 6 days before this event, we were alerting the community to its potential. Hurricanes. In 1999, we had Hurricane Floyd. It was a Category 5 storm. That's the storm right there. We had hurricane warnings along 1,500 miles of the coastline. This is the path. Florida is right over here. So you have this Category 5 storm heading towards Florida. Made the curve. We actually predicted that turn. Nobody listened to us. Okay? This was the largest peacetime evacuation in the history of the United States. Then you look at this year, Hurricane Earl, Category 4, hurricane warnings along just the Outer Banks, North Carolina, almost identical track, same turn. We made the forecast with a lot more conviction, a lot more confidence, and that's the only place that had selective evacuations with savings warned of about $700 million. This was the savings of not evacuating the area that we could have been 10 years ago. So this track and this track is about the same. Category 4 there, Category 5. Here we had warnings only 450 miles. Here we had 1,500 miles. East Coast storms. Pecos mentioned this storm. This is the President's Day storm. some people are tired of me talking about this, but this storm really did set the stage. Actually, when this happened, as you see, 22 inches of snow buries Washington, D.C. area. I mentioned yesterday, this is an area where you do not want to miss a forecast, is Washington, D.C. We had rapid cyclogenesis off the coast. That's a very intense storm. How could we miss this storm? It's on the East Coast. You have all this data upstream to initialize the models. Missed completely. 7-layer model. We weren't even using the significant level data in radiosondes. Missed it completely. So this really galvanized the research community. It really galvanized the modeling community, the mesoscale models that people were doing in the research community, like Tom Warner, who were arguing we should be operationalizing these. This was the storm that set the stage for the research and the operational communities working together. And in fact, Lance started looking at the boundary layer. I started looking at the upper level jets, and we both came together. That's where we did the synergy article. Okay, so now we get to February 4th and 11th, 2010. This is the Snowmageddon. This quote is from President Obama. I did not make up this term. Somebody else, they say there was some chatter on the internet, but this was actually came out of a White House public affairs release. Massive storm. It was actually two storms, February 4th through 7th, and then February 9th through 11th, and really buried the Mid-Atlantic region. So they had record snowfalls for individual storms for the month, all within this period. Strong blizzard conditions affect same area still digging out from the earlier storm. Storm system predicted 7 days in advance. Potential for heavy snow 3 to 5 days in advance. States implemented their COOP plans. These are your shelter-in-place type plans. And I actually remember the state of Virginia announcing that you're going to be snowed in for 5 days. Prepare to be isolated for 5 days. And I thought, as somebody who was partly responsible for this forecast, it better verify, all right? Airlines cancel flights. The retail industry pre-stock shelves. Unlike other snow events where the gross national product takes a hit, these folks actually made money because they did their sales the 5 days before the snow hit. And this is not just snow shovels. This was everything, clothes, food. I mean, if you were looking around the Washington area, this area, there was so many trucks on the road delivering products to stores. It was really amazing. So this is the storm event. Originated in the Gulf, came on out. These are the watches and warnings along the East Coast, well in advance of the storm. Very sharp cutoff. I'll get to that towards the end of the talk. But again, nice coherent watch and warnings well in advance of the storms. So I went through this yesterday. I'll do it again here. The surface analysis, the 48-hour precip event, that captures the first storm. Very heavy precip. That's 3.5 inches of water, a 3.1 over Washington, over 5 inches along the coast. Most of this was all snow. There's the low sitting off the coast. 8 to 14 days, we're indicating the potential for a storm coming up the coast. Higher probabilities in the 6 to 10 day. 3 days before the event, we do the heavy snow outline, and then with the below normal temperatures. Remember, 1970, 12-hour limit of predictability. This is 3 days before the event. So let's just go through this. What I'll do is we'll keep the surface analysis here. 7 days in advance, 6 days. Timing, okay, a little bit slower. 5 days, 4 days, 3 days, 2 days, 1 day. That kind of consistency is what allows states, because everybody's seeing these forecasts now, and decision makers are working with the meteorological community. This has become a fundamental part of their decision making. And when you're that consistent in your forecast, they take action. And again, here's the precipitation map. This is a 5-day forecast, over 2.5 inches of precip. As we approach the event, this shifted, our forecast shifted up to the north to capture the full measure. Now, the impacts, I mentioned this. I was in India at the time. I actually missed this event. I left on the last plane that left Baltimore to get to India because I was on a review panel for the Ministry of Earth Sciences. I was on the first plane to come back after the second storm, and all my colleagues have made a big joke about that, okay? So, but I got this picture. This is Baltimore. I live near this area. And what struck me about this in terms of showing the impact of our forecast, notice, that's the way it used to look like in snowstorms in the United States because nobody believed it, so they get caught out in the road. This is the way it was after this storm. So the recovery period is like almost a factor of 4. And anybody who deals with snow removal will tell you if you can keep the cars off the road during the event, they can clean it up a lot faster and get you back to business. This is another reason why people claim that the economic impact on this storm was less than what was expected. Now, so where are we in terms of our numerical models for both weather and climate? One of the things that's happened over the last 10 to 15 years is we've gone from atmospheric modeling with some in the ocean community, some in the land community, very few in the ice community, to having models that attempt to couple all 4 of these medium. So we are working, and this is what I called the Earth system modeling until I went to a conference in Boulder, Colorado about 2 months ago, and I'll show that a little bit later. But you have to have a global observing system, not only for the atmosphere, but for the ocean, for the land, and the ice, to make these predictions work, not only for the weather, but for our climate. And in this case, I'm meaning seasonal to interannual climate forecasts, which we're now doing operational. This is the computer we run on. We're now up to 73 trillion calculations per second. We'll have this computer for another 2 years, another 3 years. We will fill this computer up in 6 months. So we're actually feeling stuck, okay? And with the budget situation the way it is, we'll be lucky if we get the new computer in 3 years. We're at 3.5 billion observations per day. I told you about the global observing system being a very important part of our total modeling system. These are the number of model fields we generate per day. We have this backup system in West Virginia with a guaranteed switchover in 15 minutes, which allows us this kind of reliability. This is our on-time percentage. We're at 99.8% on time for all of our model fields. And again, our users will tell you that this is just as important as any accuracy measure that we put out for our models. They have to know that it's there all the time. This is our web access. You can actually download the fields as the models are running on these computers, and we've been doing this since 2001. And you see these winter spikes. These are the episodic big storm events. And then if you get hurricanes, you start seeing this kind of secondary max. But there's been a general increase in the access of our model fields from a diverse user community. Now, this is our model production suite. All forecasts start with observations. I mentioned 3.5 billion observations per day, 99% satellites plus radar. We are underutilizing the radar data. A lot of difficult issues for us anyway, in assimilating that. But we're working on that. Mostly, this is our remote sensing data is satellite-based as of right now. It feeds into the global forecast system, the GFS. We run this out to 16 days, 4 times a day. It provides initial and boundary conditions for the hurricane, the regional models, and our short-range ensemble forecast system, which is multi-model. It's the ARW plus the NMM, the old version of the ADA, and the regional spectral model. And then this model here drives these more local applications, severe weather, high-resolution versions of the NMM and the ARW. We have workstation versions of the WRF, both cores. We have an air quality forecast, rapid update. Dispersion model, Tom talked about this briefly. We use a model developed by ARL, and it's on call to the Department of Homeland Security and other users who need information very rapidly. We can run these dispersion models basically within 5 minutes after the call. We also run a real-time ocean model now in the Atlantic. We're going to go global. This is another community model, the HICOM model. We have a GFDL ocean model coupled to these GFDL and the hurricane wharf that we run during the hurricane season. We have WaveWatch 3. And up here is our climate forecast system. This is version 1 coupled to the MOM 3. And I'll show you the upgrade to this model in a minute. Last but not least, we have a North American Ensemble forecast system, which is the GFS and the Canadian Global. It's the first international ensemble system. It's run globally 4 times a day. With we wind up with about 160 members out to 16 days. And this is used by our weather forecasters and the folks in the Climate Prediction Center who have to forecast out through week 2. I can tell you that these 2 models here are becoming the workhorses of our forecasting community. We have a community land surface model becoming increasingly sophisticated. You can't see all that down there, but it has canopy, it has evapotranspiration, 4 different layers now down, soil types, etc. So you have a very complicated modeling system which takes us from local models to regional models to global models, all tied in to that global observing system. Now, with respect to the workstations, I noted this yesterday. I'll include it today. We do have a WRF environmental modeling system, which is actually sustained through our training group out there in Boulder, Colorado. It allows you to download fields from our GFS and then to run either version of the WRF locally. Again, this is probably part of the reason why you have users running models that don't understand models, but they're using it as a basic tool now. One of our more recent interactions internationally is with South Africa in the severe weather project, which is actually, they're now running a WRF. After downloading our GFS data, they can run their local WRFs, and they're using it for severe weather applications in Africa. And I think this just lists the types of data sets. And then these are all the countries, these are all the points which are now using that system in one way or another. I don't know if they're all using it in real time, but they have registered as users and are downloading our data. With respect to implementations, I wanted to emphasize the most recent implementation on the GFS in honor of Dr. Joseph Sella, who, of course, is a very important force in the development of spectral modeling. He passed away on February 4th, just before the big storm. And I found it ironic that the system that people were using in our country, the global forecast system, as a basis for making that 7-day, 6-day, 5-day forecast was the crowning achievement of Joe's work. So let me just mention that implementation occurred on July 28th after about 3 years worth of upgrading. We had a horizontal resolution of 27 kilometers. The major upgrades involved physics. A number of physical processes were upgraded. One of the problems we were focused on was the elimination of these false convective bombs. This one is in the middle of the country in Iowa. They were really a big problem in the tropics. It turns out that this new mass flux shallow convective scheme had a very important impact on these precipitation events. So you see the elimination of these very heavy events, and it's really helped. This is our anomaly correlation now through day 5. It's 500 millibars for the northern hemisphere. This is the monthly score. That was July. Remember, we we implemented this model on July 28th, so it is August. This is the largest monthly increase we've ever observed in our model scores. We find that in the northern hemisphere, we have a much more steady type performance now. In the southern hemisphere, which these are daily now. Okay, what I showed you before, monthly. This is, I look at this every morning. You see these kind of dropouts here are killers. If you're trying to compete with the European center, which is in red here, which has the highest score, they have the fewest dropouts. Okay? In the southern hemisphere, we all suffer, again, but they don't suffer as much as the other model fields. And you see what happens here. This is the front end of your model. This is your data, data quality control, data assimilation. And I have to tell you that the investment they've made over the last 20 years in data quality control has really paid off for them big time. So it's not necessarily the model. When people complain about the model, it's the total system that one has to be concerned about. Okay, with respect to the climate forecast system, this is a big deal for us. This is the system we used for the last 7 years, 200-kilometer analysis resolution, 200-kilometer model, 28 levels. The ocean model was the MOM3, or the simulation depth of 750 meters. Daily coupling. We use retrieved soundings from a 1995 analysis, and our reforecasts were 15 per month on a seasonal output basis. Here's where we're going. We're implementing this in early January. 100 kilometers, 64 levels, variable CO2. All the physics upgrades to the GFS over the last 7 years will be built into this system. MOM3 to MOM4, this is the GFDL model, assimilation depth down to 4,700 meters, 2-level to 4-level, daily analysis and prognostic sea ice. This will be the first system with the prognostic sea ice, 30-minute coupling, radiance assimilated, and we have 25 per month for seasonal for the reforecast and 124 months for week 3 through 6. We're really trying to push that filling in forecast skill for week 3 through 6. When we show we've done some forecasts over the last 50 years, this is the temperature trend in red, in black. This is where we were with the old system. This is where we are with the new system, with the going from a constant CO2 to an observed CO2. So we're using the observed CO2 and the observed aerosols, and you're getting a much better handle on the temperature trends over this period of time. One of the reasons why the research community, COLA, for example, actually wants the code for this model, we've delivered the code, and they're using it as part of their decadal runs right now. With respect to the MJO, I mentioned that MJO being used by the forecasters. Now, these are the principal components, 1 and 2. This is the forecast skill, again, a correlation score with a drop-off below 0.5 at day 5 with the old system. Now we can extend that out to about day 15. For the second component, we go from day 6 to about day 16. I can tell you that folks are very excited about that as well. We're really looking forward to getting this into operations. We use this for our SST forecast for the ENSO area out in the Pacific. This was our forecast from March, which was pointing to a potential for a La Nina event. It was down to about -1. Obviously, it got lower than that. Here's the most recent forecast. These are the forecasts that you get out of about a 1-month period. So 2 times per day, you get about 60 forecasts to work with. Shows a very, very narrow spread, and it's really pointing towards the La Nina holding its own, not only through the winter, but perhaps right into the spring. Okay, the forces for change. One of the major forces, and this is what I emphasized yesterday, if you're going to hook up with decision makers, you have to give probabilities of your forecast. If you go 50-50 all the time, decision makers don't use your forecast. If you go 60%, if you're dealing with 20s and 30s, and then all of a sudden you pop up to 60 or 70, they start using your forecast. The ensemble system allows you to do this more effectively for parameters. There are actually folks doing model output statistics now on the back end of ensembles to try to get into this probabilities for decision makers. Okay, so saying that, one of the drivers for this now is the ensemble forecast system. And what we're seeing is an increasing drive towards multimodel ensembles, not just perturbing the initial state with a single model, but working towards a multi-model. So for our short-range forecast, we have the SHREF. Remember I said we have 4 models running in there. We're going to work our way down to two versions of the WRF, but still multi-model. Multi-model here, 2 to 3 model systems. The climate forecast system, we've just signed up to join EuroCIP, so we'll be joining the European Centre, Météo France, and UK Met within the next year. We'll be doing our seasonal forecast off of a 4-model ensemble. So this is really a very important change for the way we're going to run our modeling system. I can tell you that in the requirements for the computer we're running today, which was written about 10 years ago, the word ensemble didn't even appear in those requirement statements. So this is a major shift, a revolutionary change, actually, in the way numerical models are being used for forecasting. We're entering, this is the what's left of the NPOs. We had a very rough procurement of our next satellite system, the JPSS. It's not only hyperspectral data, but we'll have access to data in 23 minutes to a half hour that now takes 2.5 hours. So we'll have that much more data to work with in our initial state. If we can have data assimilation systems that can run more efficiently, we can initialize our models sooner. All models will be run within the Earth System Modeling Framework, so we're standardizing our code for exchanging model code with the research community and finding a more efficient way of dealing with ensembles. And also, all our coupling amongst the various components of the atmosphere, land, ocean, etc., will be done within the Earth System Modeling Framework. Model data will be accessed through this NOAA Operational Model Archive and Distribution System, NOMADS. Allows you to subset exactly what you want, so you don't have to take the whole data set. You just come in and take what you want. And then the Operational Earth System Model, I've mentioned that. We're trying to enable more explicit hydro, ocean, coastal, climate, and ecosystem applications. And this is one of the major future areas for all of the community, is extending prediction into those areas. I mentioned the multi-model ensemble across the whole scale. This is what we'll be running by early next year. We're adding FinMOX, no gaps, to our system. We have 4 models here, and we're joining EuroCIP within a year. I mentioned the importance of the forecast for New York. We all focus, of course, on the heavy snow in the Mid-Atlantic, but look at this, how the warnings just stopped right there in New York City. Very sharp boundaries, so there was a lot of millions of people who were not warned for this storm that probably would have been warned even 5 years ago. And the key model fields that allowed us to shift this to the right was the SHREF, the Short-Range Ensemble Forecast System. This is 3 days prior. You see the spread in the position of the low. By the time we got to 2 days and then 1 day, very sharp, they all converged to this turn. So with a lot of confidence, we told 50 million people in this whole area that the snow line was going to be cut right there, and it turned out to verify. Okay, extending capabilities. I showed this before. Atmosphere, ocean, land, cryosphere. I go to a conference, and the research community is defining the Earth system as involving biochemistry. We're just feeling comfortable with starting to couple this. We have to bring this. And building direct linkage to the forecast of what I call critters. Actually, Margaret Davidson calls them critters. Fish, seafood, shellfish, that kind of thing. Built right into the system, predicting what's going to happen to them as you're making your predictions. So an example, we had the big oil spill in the Gulf of Mexico, and there were all kinds of models being run to show where this spill was going to go. And in fact, I believe it was the NCAR model was used and shown on TV, which showed this oil wrapping around Florida and going right up the East Coast. It caused a big stir in the country. The folks up at GFDL started working with the, they were doing this biological decay of the oil. And once they included that in the predictions, this is the distribution they got versus this without it. And, you know, the big controversy now and the big research that's going on is, where did all the oil go? Okay? And there are those who believe this is a very important part of where the oil went, was eaten. We can do this in real time. We could actually build this into a forecast. We're doing ecological forecasting system experimentally, the Chesapeake Bay. We don't want to turn this into a dead zone. So there are beach and water quality forecasts now being made, living resource distribution, dissolved oxygen predictions, harmful algal bloom being predicted, disease pathogen progression. We're testing all kinds of experimental systems here. There's also work being done in these other areas. I can show you a forecast that's made for sea nettles, jellyfish, which are very painful to swim in, so you don't want to go swimming in there that day. But more importantly, there's a nuclear power plant right there, and the intake of water is blocked by sea nettles, and they operate differently when they know sea nettles are there. They can plan their operations if we provide them a prediction. We're doing this in cooperation. In fact, we're enabling ocean services to do this. We're not doing this directly out of NCEP. There are other components of NOAA doing it, but they're building off of our predictive systems to make those kind of predictions. Last, this envisioning the future. We're going from basically assessments to prediction, and that's the key word here, that people are actually getting into these different areas in a predictive mode. So air quality, using chemical and particulate matter, from regional to global. Tony Hollingsworth actually led the way here at the European Center. We're catching up to where they are. Hydromet, you look at water quality and beach quality forecasts, they're usually tied to a heavy rain event. So if you can predict the heavy rain, you can predict the runoff, you can predict the water quality and the beach quality. Energy planning, temperature, wind, sunshine forecast, this is, Tom was alluding to that. Marine management, longer-term climate and shorter-term weather forecasts for these critters. The sensitivity of these different fish and shellfish to these types of parameters that we can provide is well known. And then health factors, longer-term climate and shorter-term weather forecasts. And in fact, we're working the Africa situation for meningitis, north winds correlated to meningitis outbreaks. In this area, there's a sociological reason why this happens. I won't go into it here, but if you can predict these fields, you can actually start putting out alerts for what to do or not to do. The waterborne diseases in Dakar, Senegal, there's a correlation with about a 3-day lag between the rainfall and cholera outbreaks. So we're working with them in that situation. Okay, so in summary, advances in weather prediction have been astounding, especially for extreme events. Short-term climate, we're predicting ENSO events now, and with our increasing understanding and predictions for MJO, I suspect that we'll be doing these types of forecasts for at least the potential of extreme events 30 days in advance. That's one of the visions that we have. Rapid advances in the current model suite. There's more of a focus on the multimodel ensemble approach, and I think this is going to make a weather forecast out to 10 days in a routine manner within our reach, not just for extreme events, but for all weather parameters. We're on the front end of extending prediction capability into many areas. I've listed them here, and if you, again, think back 30 years ago, meteorology was ridiculed for building prediction as a fundamental part of their science. Now everybody's rushing to sort of hook on to us for this predictive capability. And then the success will be based in large part on our willingness to expand these prediction enterprises. There are a lot of meteorologists out there who want to just stick with our core functions and not get into these areas. We have these discussions all the time in the U.S., and I've seen it in other parts of the world. But it's very clear now that we can correlate these predictions into other areas and make it useful for societal decisions. Thank you very much. Good. Good.
statistical downscaling.
Right.
To European models usually don't follow this policy. So what will happen with this joint?
Yes, great question. That's why it took over a year to negotiate the interaction. But first of all, we convinced all the partners in Europe that by adding our model, we actually added to the skill levels at the back end for the products. And likewise for us, the three models add to ours. So what we agreed is that we cannot distribute the other models. The distribution policies of the models themselves are a function of those centers. But we can, whatever products we derive from the combination of the four models, we can distribute those products. So we don't have any, there's no inhibition to release products just because there are three other models, but we cannot release the model fields from the other centers.
In one of your slides, it was mentioned that NOR, land surface model, is driven by observed precipitation data. And in addition to this, at least several years ago, I think your service was, your institute was the only one in the world using observed precipitation in the initialization procedure. If the situation remains such that you are the only ones, and how important this information is for your situation?
Yeah. I can't tell you whether we're the only one or not. I know we were the first, but it's very important. The soil moisture, soil type, soil moisture is a very important parameter that helps drive local circulations. And then over a long period of time, for the longest simulations, the feedback mechanism, because now we're into active coupling with the land model itself, is a very important part of the predicting system. So we're doing that. I know that we've had problems in we've done it knowing we have certain problems in the boundary layer because, this is still a wide open field in terms of not only the observations, but the understanding of how it couples. But the boundary layer predictions were better, even with those crude first attempts, than what we had without it. Significant changes in the max-min temperatures, the wind fields was a very important addition. Ken Mitchell was one of the people who helped lead that effort.
Thank you very much.
Okay.